Good afternoon, ladies and gentlemen. Introducing my group members. Marina Luis and myself, Mina Hani. Our thesis research topic is self-compacting complete. Our presentation is outlined in the following points: introduction and background, work objectives and scope, research methodology, expected outcome, anticipated challenges, and time schedule. Vibration or compaction is a vital stage of concrete pouring, where the vibrator introduces pressure waves inside the concrete, allowing the entrapped air bubbles to rise to the surface, enabling the concrete to settle firmly in place. This process has several medical implications on the user, such as sprains, strains, and fractures, white finger disease, and breathing difficulties from the fume from the vibrator itself. So why using SCC or self-compacting concrete? Pouring concrete or compacting concrete is not always feasible in narrow sections, such as corners, dense reinforcement, such as in slabs and beams, unskilled, untrained labor, and lack of proper supervision during vibration. SCC was first developed by Dr. Okamura and his PhD student Kazan in the University of Tokyo in 1982. However, it was first implemented in North America. SCC has the following characteristics. Its viscosity is fairly modified. It has low fine to coarse aggregate proportion, and it's somehow flowable. It's more flowable than conventional concrete. And now my colleague Marina will continue with the report of the group.
As for the work objectives and scope, we will examine properties of SCC made with innovative materials. We will study challenges of mass production of such concrete in Egypt. Different mixes of the following materials are going to be used: low water cement ratio, super plasticizer, viscosity modifying agent, and silica fume. As for the advantages, first, no vibrations are needed, unlike in the traditional concrete. No repair is required. Higher strength and durability of the concrete. The ability to pour concrete in inaccessible places, and reduce construction time and labor cost. For the advantages, high cost in production. The concrete is highly sensitive to variation in material. Segregation of aggregates may happen, and the concrete is highly sensitive to volumetric changes in material. And now I will give you my colleague Basil.
As for the mix designs, we have 5 groups of mix designs, summing up to a total of 10 mixes. The first group will be our base reference. We will have the concrete and adding two types of super plasticizers from 2 different suppliers. The second and the third group will be having the super plasticizer added with 2 different viscosity modifying agents from 2 different suppliers. We will test those on 2 different water to cement ratios. The fourth and the fifth group are adding super plasticizer, 2 different viscosity modifying agents from 2 different suppliers, and silica fume. We will check the addition of the silica fume to the properties of the mix and the concrete, if it will enhance it and to what extent. And then we will try this on 2 different water to cement ratios. For the testing, we have 2 different categories of tests. The first test is the aggregate testing. We will test the sieve analysis, the unit weight, and the moisture content. For the aggregates, we have to have round aggregates, not angular or semi-angular aggregates. For the concrete testing, we have 2 different groups. The first is the fresh concrete testing, and the second is the hardened concrete testing. Now I leave you with my colleague Magdi for the concrete testing.
Concrete testing is divided into 2 parts. We'll test concrete when it's fresh. We'll start by the unit weight, specific gravity, air content, and temperature test. Then we'll have the special tests of the self-compacting concrete. We have the flowability tests. We have the slump flow test, the V-funnel test, and the T50. The slump flow is shown in the picture, where we measure the horizontal, not the vertical, as the traditional slump. Also, we have the fastening ability test. We will start with the L box, then the U box, and the J ring. The L box is shown in the picture, where we will open the gate from the vertical side to allow the concrete to pass through the rebars in this side to go to the horizontal, and then we'll take the ratio of the height from the horizontal and the vertical one. Then we'll have the segregation potential test, because our concrete is characterized by high viscosity, so we'll test the seal stability and the penetration test. For the hardening concrete, We have the compressive strength test. We'll have it at 7 days, 28 days, and 56 days if possible. Then we'll have the flexure strength at 7 days, 28 days, and the corrosion of reinforcement, and the chemical durability and permeability of this concrete. Our expected outcomes from this project that we are seeking recommendations for optimal high performance self-compacting concrete, and highlighting properties of self-compacting concrete when it's fresh and hardened, and we'll test the durability of this concrete over the years. Then assessing the cost-related problems for self-compacting concrete. After that, we'll conduct the non-traditional tests as mentioned previously in the slides. Then exercising the teamwork skills and the time management of this group. Then my colleague Khaled will continue the anticipated challenge.
From our research and from the literature reviews we've been looking at, we think that we're going to anticipate some challenges that we're going to face. First of all, the acquisition of suitable material in a timely fashion. Unfortunately, the material we're going to be needing throughout the scope of our project is not it's not found in Egypt, like it's nowhere found. So we need to get these materials from different suppliers, special suppliers. Next is the manufacturing of the formworks and testing equipment needed. As you saw in the previous slides, the tests needed for testing self-compacting concrete aren't exactly normal tests that you would find in the lab, or not exactly equipment that you'd see every day, so we need to manufacture those equipment ourselves. And as we're working with a new material, there isn't much experience in the field of self-compacting concrete here in Egypt specifically, so we're going to be revising the new material and hopefully finding new results. This is a general time schedule that we came across. This should be putting the 15 weeks to the scope of our work. We've been working on the literature review for the past 3 weeks already. As you can see, the presentation dates are highlighted on week 3, week 19, and week 15. Material acquisition has already started. We have already acquired the viscosity modifying agent that we need, which is called Viscocrete. It's from CENG. And material testing is going to start at the beginning of next week, inshallah. That is going to be general testing, just simply for aggregate testing and material testing to know the exact specifications of the materials we have. Experimental work is going to start at the beginning of the fifth week. This is going to be accompanied by the results and analysis 1 week later. Aside from the fresh tests that we're going to be conducting, of course our cubes, we're going to start crushing cubes from 7 days after pouring the concrete, 7, 28, and 56 days if possible. So we need to leave sufficient time so we can crush our cubes before the end of the semester. We're going to conduct a couple of field visits, hopefully to some mixing plants, Lavage and Zika, to see the self-compacting concrete in action. And of course our research paper is going to go with us from this week onwards until the end of the semester. These are some references of our literature reviews. Thank you very much.
I have one question. How are you going to test the corrosion of the reinforcement?
I think we actually discussed this case with our advisor, Dr. Abu Zaid. We said that we won't go into very much detail as it will take us out of scope testing the corrosion, but we haven't settled on something specific yet. But we said that we're going to test it in some corrosion tests, but not in very much detail.
Excuse me, I want to add for my friend that we'll use sulfate to test the corrosion in the steel of the...
So we're going to do accelerated corrosion test?
Yeah.
Somehow?
Using sulfate.
I mean, using some kind of cell, electric cell or something?
Until now we didn't read this part, but with more research we'll get the way to...
I just have one question, maybe you can think of it. Are there any limitations where I can use the self-compacting concrete, for example, if I'm casting a pipe or I'm casting a column, how long it can be or how deep it can be so that I can say that after this limit it's no longer applicable or it can go that far. This is also will be very useful for the application itself. Also, will it have any impact on the structural behavior of, for example, slabs? If I'm casting slab on grade or slabs without compaction and depending on the concrete,
Mm.
will it have an impact on the behavior of the slab, on its strength? Will it be better,
Well,
less,
actually,
the same? I mean, yes.
we are actually doing the tests to see if the compressive strength and the flexural strength are as required by the design or not.
Yes, that's on a specimen, but how about for the member itself? I mean, if we cast a beam or a column or
We are gonna be casting a beam, inshallah, and
maybe it's
we'll
out
try
of scope, maybe it's out of your scope.
no, we will cast a beam, and we'll try to relate the results we get from breaking the beam, of course, compressive and flexural strength, to how that concrete would perform in slab condition or in whatever condition we
I guess self-compacting means that you rely that as you cast the concrete for somehow a deeper section, then the movement of the gravel and so on, along with the material that will improve the viscosity, will lead to concrete that does not require vibration and so on. Then when you really say you're going to test cubes, how will the cube somehow develop its own self-compaction? You just you pour some concrete into your cube and then you test it. Is there a sufficient chance that a cube with a small height will develop its own self-compaction?
I get your question. I believe that cubes focus on mainly the compressive strength of the concrete behavior. But regarding, let's say, for example, aggregate segregation or such factors that may come into play, we have special tests that are designed for self-compacting concrete, like the L-box test that my colleague has told you about, the funnel test. These special tests are actually designed to check these specifications exactly that you're asking about. Like, for example, segregation of aggregate, the length, for example, concrete may fall through before it behaves differently. So, yes.
To follow up on that, I think there is a test that you have to do to complement what you are doing. I agree with Dr. Ahmed Imam. All what you have done, whether it's beams or cubes, you are talking about 15 by 15 by 15 cube that's right in the ground, so the effect of the self-compacting is not there. The test that you should do, and I require to see that in your proposal, you have to cast 15 by 15 by maybe 75 or 90 centimeter long column. And you cast that vertically. And after you finish it, you slice it. If that's 90 centimeter, you slice it into, using the saw, slice it into 6 cubes. And tell me, what's the difference in the strength between the top cube, the second one, and the bottom cube? In this way, you can really convey the information that you want, that the self-compacting concrete is working and there is no segregation, such that I have only mortar at the top and I have the coarse aggregate all at the bottom. So this test is more important to me than you make 5 or 6 different mixes. If the scope of work is going to be large, maybe reduce the number of mixes, but this must be one of them. And the other thing I would like to see, you mentioned some of the references. AUC is one of the places that this test has been done under the supervision of Dr. Naguib. So I like to see this as reference also in our work, because we are as good as the other rest of the world that are doing in this work. So this work has been done and we started investigation in that. So please include in your scope of work casting the whatever 60 or 90 centimeter long column and slice it into different cubes, mark them and number them, and tell us one of your graphs what is the variation in the strength and in the density with the variation of the depth in that column. Okay,
Thank you very
you.
much.
Any other question? Thank you.